Happy to welcome ALICE Patania, who's going to talk about predicting emergent sequences of neural networks via directional graphs. ALICE?
Hi, thank you very much for inviting me to give this talk and present our work. This is the first time that I present this work, so I hope everything is going to be clear, but if you have any questions, please interrupt me and ask them. And this is a joint work with a group of women mathematicians in computational topology. We started this work at a workshop in 2019, and we are writing up the results right now in these days. So let us know what you think about it. As Catherine said, I'm going to talk about neural networks dynamics. And in particular, I'm going to talk about trying to predict emergent sequences using what I'm going to introduce as directional graphs. So before I start, okay, what are neural networks? In this case, neural networks are networks where are graphs where the nodes represent neurons, neuronal cells, and the connections are actual physical connections between these neurons. And the idea is to try and build a simple and easy to understand mathematical model that it's gonna help us understand how these neuronal cells fire up as electricity goes through them, as you can see in this animation. And when these population of neurons fires together or in sequence one after the other one, and try to understand how the different dynamics emerge from their connections. The model that I'm going to talk about today is called the differential linear network model. These are very commonly used, easy recurrent networks model that are defined through the system of ordinal differential equations that I show here. In the ordinal differential equation, the way that they transcribe the neuronal activity is by encoding the change in the firing rate of each neuron, which are the nodes of the network, and that is represented here as xi. And then the firing rate is changed according to the value here shown in the square bracket here, and which is given by the connection strength of neuron I to all its its neighbor neurons J, and with together with an external input that comes from outside of the system that can be directed to one specific neuron or node, or it can be to the entire system. It can be constant to the entire system. This kind of dynamic is dependent mostly on this matrix W, that describes the connection between the different neurons. In our case, I'm gonna we focused on the case in which the elements of this matrix are all negative or non-positive. In this case, these are called competitive networks, since every interaction that a neuron has with its neighbors, it's going to try to dampen its firing rate and make it die down and not fire anymore. We focused on a very specific kind of competitive TLNs, which are called combinatorial pressured linear networks. These models are special because they depend, their dynamics depends mostly on the connections between the nodes in the graphs more than the values itself that are in the matrix W. The basic idea behind this the CTLNS model is to model a network of excitatory pyramidal cells shown here as triangles, and these excitatory neurons are connected with each other through very weak inhibition connections. So these connections are going to dampen the firing rate, but in a very low, with a very low strength. And the assumption is that in the background, all these excitatory neurons are going to try to be dampened very strongly by some cells that we don't know about, that are these gray, unknown variables in the background. So what we know, it's this graph G, which connects the different excitatory neurons, which are the only things that are firing up. And we know that they are weakly connected with each other, so they try to dampen each other out in a very weak way. And in the background, we have a very strong inhibition system happening. To model this biological kind of dynamic, the matrix W, it's defined via the connections in the graph by adding a value that it's constant between 0 and -1 for every time there is a connection between these excitatory neurons, and a value that it's greater than 1, that it's smaller than -1, sorry, every time that there is no connection. So we model a very weak connection when there is an edge, and a very strong connection when there is not an edge. And the only 0 values are along the diagonal. So each neuron doesn't dampen itself out if there is no dynamic going through it. Because the matrix W is completely defined by the connections, the dynamic that comes out of these CTLNs, it's actually completely dependent on the graph itself and not on the parameters epsilon and delta. And not on the parameter epsilon delta. The reason why it's very important to study these kind of networks is that when one usually studies threshold linear networks, or TLNs, it's very hard to decouple the connectivity between the effect of the connectivity between the neurons and the effect of the ordinal differential equation themselves and of the dynamics themselves. And by studying the combinatorial threshold linear networks, we are able to decouple the connectivity and the dynamical response and understand which part of the dynamics is solely dependent on the connectivity and which part of the dynamics instead might be dependent on the matrix W. So the hope is that by studying the dynamic that it's dependent on the connectivity, we will later know much more how important it is for neurons to be connected to each other or not in neuronal dynamics. Even though combinatorial threshold linear networks are very simple and very constrained, as I've shown before, the parameters epsilon and delta have a very small range of values that they can take, and the matrix W has a very fixed structure. The dynamic that comes out of them, it's still very complex. It can still be very complex. There is here you can see an example of a CTLN that has a wide range of nonlinear dynamics where we can find both multistability with different fixed points and different neurons firing together at the same time, a limit cycle, and chaotic and quasi-periodic dynamic. And in order to understand when some nonlinear dynamics emerge and when others emerge in the network, the standard way is to look at the fixed points of the matrix W at the of the ordinary differential equation and its system. So these fixed points are the points where the dynamic doesn't change and is fixed. And if we take a small variation of in a neighborhood of these fixed points, we are able to fall into one of the dynamic attractor and understand better the dynamic. So being able to recognize which are these fixed points and being able to understand what is their support, it's very important to then study what kind of dynamic it's gonna come up and which neurons are gonna be part of the dynamic. In here, I showed the example from before with all the different the full range of dynamics that it could have, and on the right side, these are all the fixed points that can be found by solving the system of ODEs. And if we take, as you can see, there are a lot of fixed points, but before I showed you only 4 different kind of dynamics. That is because not all fixed points are stable. Some of them are. So if we start on those, on a small neighborhood around those fixed points, we will always stay and end up in the fixed point attractor, and the dynamics is going to be stable on those points. But others are unstable, and even though we start on those fixed points, then the network is going to vary, and the dynamics, it's going to vary, and it's going to fluctuate between different attractors. In this case, the dynamic shifts between different cyclic attractors, and even though the understanding between fixed and points and between stable and unstable fixed points is important, we are gonna focus right now only on finding the possible support, because in both cases that I've shown here, even though the fixed points are unstable, the discovering the fixed point, which neurons are defining those fixed points, which nodes are the ones that define those fixed points. It's important to understand which are the neurons that are part of the firing sequence, that fire in a sequence one after the other one. So unstable fixed points help us understand what is the sequence generation and how that sequence generation comes up in the dynamic. So my goal today is gonna try to convince you that there is a way, given a huge graph and studying only its graph properties, to come up to understand which subset of its neurons are going to be part of these sequence of firing neurons that we can see in the dynamic. And this work is not new. In 2019, Curto, Jennison, and Morrison already came up with a set of graph rules that help to understand when a motif in a graph can support or not support the fixed point. And here you can see an example of all the different rules that make a motif either a permitted motif where a fixed point can survive, and a forbidden motif where the fixed point cannot survive in that configuration of nodes and edges. And so our our aim when we started working on this project was trying to, given a complete graph, try to isolate which graph architectures in which in its subgraph can support sequence generation. And to do that, it's kind of the opposite of these rules by Curto, Jennison, and Morris, where they took smaller motif and combine them together to get bigger motifs that can still be permitted motifs for the support of fixed points. And our idea was to try and backtrack that and come with, starting with a very complex motif, can we find smaller motifs inside of it and a way in which they can be combined that can tell us something about the dynamic and about the support of the fixed points. These smaller motifs are the most important part in understanding the dynamic, and they are called directional motifs or directional graphs. And the idea behind directional graph is trying to find particular graph motifs in which we are sure what is going to happen with the dynamics. In this case, in the case of directional graph, what we are interested in is being able to partition the node of the graph into a subset of the graph that will never support a fixed point and a subset of the graph that might support the fixed point. So a directed graph G is called directional if it can be partitioned into two subsets, omega and tau, such that a subgraph of the vertex set that intersects omega dies by domination. These means that by the graph rules that I showed you before, this subgraph cannot be a permitted motif for the support of a fixed point. And this means that any fixed point is going to be always be contained in the tau. Yeah. And here are some examples of directional graphs. And as you can see, the most simple directional graph that we can have is the simple edge, directed edge, where any kind of the only sigma that we can have is that contains omega is 1, 2, and there the dynamic is going to always flow to 2. And but there is a wide range of different directional graph, and it's not always graphs that have a lot of edges going towards tau that make a graph directional. We can have, like in this case, graphs where we have the same number of edges going to omega and to tau, up, back and forth, and still the dynamics is constrained to tau. And the same goes for more complex dynamics, like here where we have a cycle, still with the same number of edges going upwards and downwards. The dynamic is constrained, it's always constrained to the tau, to 4 and 5. And below you can see some example of graphs that are not directional, even though they have a lot of edges going downwards, like in this example. We still have free edges. It's the same as the example on the top, but we added one backward edge. And this backward edge changes the dynamic, and now the fixed points are not contained in tau anymore. And the same goes for these examples where we removed some of the backward edges that go up towards omega, and still these networks are not directional. They actually have a full support, which means the entire network is part of a fixed point. Even though all the the direction of the edges would make us think that since all the edges go down to tau, the dynamic is going to flow downwards. So it's not that easy to understand when a graph is directional or not directional. And it's not as intuitive as just dividing a partition of the nodes into the edges that are going to go from one to the other one without any back edge. And but once we have these directional graphs, we have the certainty that the dynamic is going to go a certain way. So we can use these directional graphs to understand better where the dynamic is going to go in the larger graph. And the same paper by Curto, Jennison, and Morris, they introduced this idea of a weakly cyclic graph, which is a graph that it's composed of directional graphs that are chained together in a cyclic manner. So these would be graphs where the dynamic flows one way. We are certain of that, and because they're chained together, the dynamics it's going to flow cyclically. So here you can see an example of a weakly cyclic graph. The bottom and the top are the same two nodes, 1 and 2. And when we look at the dynamic, we can see that the weakly cyclic decomposition actually predicts the sequence of the firing of the neurons. And we can see that neurons 2 fires, and then 3, and then 5, and then 6, and then 7, and then 2. And these smaller nodes that start firing and then die almost immediately, that are here highlighted by being underlined, 1, 4, and 8, are actually the periphery structure of the main nodes that are firing. So the main cycle, it's 2, 3, 5, 6, 7, and 2. And as 2 fires, 1 starts firing together with 3. And then 1 gets dampened down by the background edges, while 3 keeps on firing up, and then initiates the firing of nodes 4 and 5. And then 4 is dampened out. And then 5 keeps on firing, and it goes to 6 and 7. As you can see, as 5 here in blue ups up, there is no smaller bumps down here. There are no other edges. That's because 5 and 6 don't have any periphery nodes that are getting activated. And then once we arrive in 7 again, then we start having again these periphery nodes, 8, that starts again before being dampened out by the background inhibition dynamic of the network, strong inhibition of the network. And we can predict the sequence just by looking at the graph and at the decomposition of the weakly cyclic graph. So the idea is to take this concept of the weakly cyclic and generalize it to a more general graph. If we have a general graph, can we use directionality and directional motifs to decompose the graph and understand from the local dynamic of the directional graph something about the global dynamic of the more complex graph? In order to do this, we have to understand what happens to the dynamic when two graphs overlap with each other and they have an intersection. So here we introduce 3 different kinds of overlap that we can have between directional graphs. These are called chaining, merging, and splitting. Chaining is when two directional graphs overlap by having the tau equal to the omega. So as the dynamic flows in G1 from omega 1 to tau 1, it's actually the omega of another graph. So the dynamic will keep on flowing from the omega 2 of the graph to the tau 2 of that graph. And this will create another directional graph where the tau is the tau 2. Merging is when the taus, so the place where the dynamic ends up for the two graphs coincide, it's the same. So the dynamic can either flow from omega 1 to tau 1 or from omega 2 to tau 2. And if they intersect with each other, we can consider the full graph as still being directional with the same tau as the two original directional graphs. And splitting is instead where the dynamic can start from the same omega, and then it can flow down to two different taus. So the two graphs have the omega part in common, and we can see the union of these two graphs as still a directional graph, where the tau now it's the union of the two taus that we begin with. So here you can see an example of a weakly cyclic graph and how these free graphs, G1, G2, and G3, are chained together. So the taus and the omegas overlap with each other, are exactly the same. And as they are chained one with the other, we get this weakly cyclic graph that we showed before. So as I said before, if G admits a graph cover that has a chaining, a merging, or a splitting, then it's still directional, but we can actually generalize these concepts to n different graphs. So if G admits a cover where every two consecutive graphs intersect by chaining, then we will have a very long chain where the dynamic is going to flow from the first omega 1 down to the last tau of the chain. And the same goes for merging. We can merge n number of graphs if they all have a tau in common, and we will just get an omega that it's as big as the union of all the omegas of the graph. And the same goes for splitting. If the graph G can be covered by n graphs that have an omega all in common and different taus, then the graph G is directional with the common omega as the beginning of the dynamic and the union of the taus as the target. But these example of covering of a graph, even though they can be very helpful, they're very limited in the kind of structures that one can find. So in order to better understand the dynamic of this large graph and how we can cover it with a directional cover, we are going to introduce the concept of directional cover, which is a cover that it's done with directional graphs Gij and with a non-trivial partition of its vertices. And a graph Gij in the cover must be directional, with the direction going from nu I to nu j in the partition of the vertices of the graph. And if two graphs in the cover intersect with each other, then they're either merging, chaining, or splitting, so that we are certain that the dynamic is gonna flow a certain way. And the example of the weakly cyclic graph that we showed before, it is actually an example of a directional cover. And so once we have the directional cover, we can study and understand the dynamic better by building a nerve of this cover. A nerve of a cover is a directed graph whose vertices are indexed by the partition nu that we described before, and the edges are defined by the graph covers Gij, where we have an edge from I to J if the graph cover has a directional graph G that goes from nu I to nu J. And as you can see below, that's the example of the weakly cyclic graph. It's gonna have as a nerve simple free cycle, and that explains the weakly cyclic dynamic that emerges from it. And we denote as pi the canonical quotient map that goes from the vertices of the graph G to the vertices of the nerve, which is gonna assign to every vertex of the graph I of the graph G, the index of the nu I that contains the vertex in the partition. So a trivial example of a directional cover that we can have in a graph that has no bidirectional edges is the cover that it's made up of the most simple directional graph that we saw before, which is the edge. And as you can see, the graph G cannot have bidirectional edges, as bidirectional edges are not directional graphs, hence they would not cover the original graph. But if we can cover with this trivial example, then the nerve of the graph G is going to be the graph G itself. And if we can find more complicated directional covers, then the nerve is going to start telling us something more about the dynamic of the network. So before I go to the main results, I would like to ask if anybody has any questions. Okay. I hope that's a good sign. So now that we have all the elements, we know that we have these directional graphs, which are the motifs where we know the dynamics goes a certain ways, flows in a certain way. We have knowing when two directional graphs overlap in an allowed way, so either by merging, splitting, or chaining, then we know what it's going to happen to the dynamic and how the dynamic is going to flow. Now that we have these three components, we can start studying the dynamic of the entire graph. So before we look into our main result, I'm going to introduce one last definition, that is of the DAG decomposition of a graph. A DAG decomposition of a graph, it's a partition of its nodes into two sets, disjoint sets, W and T, such that T must be non-empty. The graph restricted to W is a directed acyclic graph, and the graph restricted to T contains all the sinks of the directed acyclic graph defined by omega, and there are no back edges that go from T to W. And this stack decomposition can be minimal. That is, there is one decomposition that has the smallest possible subset T in the partition. And we are going to call W the DAG component of the graph and T the non-DAG component of the graph, just in case that's how I'm going to call them afterwards, and I'm going to forget that I didn't explain it. And we can always find a DAG decomposition for a graph. In worst case scenario, W is going to be the empty set if the graph does not have any subcomponent that it's directly acyclic, but we can always find one. And not only that, we can always find a minimal decomposition for the graph. So now that we have a way of decomposing the graph into an acyclic part and a non-acyclic part, we can go to our main theorem, which is given a graph and its nerve found through the directional cover, we can, if we have a DAG decomposition of the directional cover of the nerve, then all the fixed points of the graph are going to be contained in the contour image of the fixed points of T. This means that we are able to reduce the possible support of the fixed point of an entire graph G to only those nodes that are part of the contour image of the non-acyclic part of the nerve. And I'm going to try to give you a general idea of the proof, that it's also going to help you understand the theorem itself and how it works and why it's so important to understand the fixed point structure and support of the graph. The idea is very simple. We're going to use 3 lemmas. The first one is that if we have a graph G and its nerve, and if the nerve has a proper source, that is a node that has at least one outgoing edge and no incoming edge at all, then the graph G is directional, with the omega being the contour image of the proper source S. So if we have a proper source in the graph, we know that the graph is directional. So we know that the dynamic is going to flow in a certain way in the graph, and we can restrict the possible fixed point supports to the tau of the directional graph G. The second lemma is that if a graph has a nerve DAG decomposition into omegas and taus, we can find an ordering of the vertices of W, so that if we remove the first node and if we remove the nodes sequentially according to the ordering, the first node, it's always going to be a proper source of the resulting graph. So you can see it here. It's easier to show than to tell. If we remove the graph S, then 1, 2, and 3 are still going to be proper sources of the graph. So if we remove 1, then 2 or 3 are still going to be proper sources. And then as we remove all the nodes in omega, we have a sequence of nodes that are always going to be a proper source of the graph that we can remove and find in the nerve until we are left with an empty W. So now it should be quite easy how having this sequence of proper sources and having the lemma from before that tells us that we can restrict the fixed point support to the tau of the G when we have a proper source in the nerve of the graph. How we can iterate lemma 1 and 2, one after the other one, keep on finding the proper source, go back, and keep on restricting the tau of the graph G until we only obtain tau. However, this is not complete with only these first 2 lemmas. That is because once we remove the first proper source S, lemma 1 tells us that the new graph G minus the contour image of the proper source we've removed is directional, not the entire big graph G that we started with. So we need a third lemma that it's going to allow us to grow the graph again back to G and keep the directionality that we found with this new ordering of the vertices. So the last piece for the puzzle for our proof, it's going to be that if we have a graph and its nerve, and we have a DAG decomposition, we can find an ordering of the vertices in W, in the DAG component of this decomposition, so that all these vertices, one after the other one, are going to become a proper source of the graph. Then G is directional, with omega being the union of the contour images of the source. And actually, G is going to be directional with a union of any number of these sources taken sequentially. But if we take the union of all these sources, then we will find that G is directional with only T being left. And that's how we prove the theorem. And so we start with the first proper source S, and we find the first omega being only the contour image of S. And then we slowly peel off the second source, S1, and then S2, and omega keeps on growing in the directionality of the graph until we are left with an empty W, and the omega of the graph is all the contour image of W. So what the directionality of G tells us is that if we have a subset of the vertices that intersects this omega, then this subset cannot be a support for a fixed point in G. This means that if we have a subset that we know it's a fixed point, then it cannot intersect omega in any way, which means it must be fully contained in the contour image of T. And that is what the lemma was claiming. Hence, we have proved that. So going back to our initial idea, how is this going to help us? How is this theorem then is going to help us to isolate the architectures in a graph that support sequence generation? So we have the adjacency matrix of a graph. We can build a CTLN dynamics on it, and we are going to see that the node seems to have some sort of periodic structure, but they all seems to contribute in a way to the dynamic, as we can see in this little video. How can we find the support of this sequence, and how can we describe it in a way that it's easy to characterize? So in summary, using the theorem, if we have a graph G, we can try and restrict the possible support using a directional cover of the graph, as the one shown here. And then when we build its nerve, we can see that the dynamic is gonna flow from the node in purple here down to these three nodes, which are connected with each other in the nerve as a cycle. So we're gonna predict that the dynamic is gonna have a period sequence that it's gonna go from the nodes in red to the nodes in greens to the nodes in yellow and back. And it's not gonna contain any of the nodes in purple. So when we actually look at the dynamic with this new reorganization that comes from our graph, then we can see actually that that's actually what it's happening. The dynamic follows the cycle in the nerve, and we can see how the sequence emerges, and we have the same core periphery structure that we saw before in the weakly cyclic graph, that also here it emerges. And even though we have that some edges from the red nodes go back to the purple, as you can see, there is no presence of that core periphery structure there, because the dynamic is fully contained in the cycle of the that the nerve has described. Oops. So in the future, we intend to keep on studying these directional covers of a graph, and to further characterize the fixed points that are the fixed point supports that are contained in the T part of the graph. And in the same way that we were able for the weakly cyclic graph to completely predict the sequences that arise, we would like to do that for the general non-acyclic component of the graph. And that's what we're studying now. So if you are interested into this subject, we don't have the paper out yet. It's going to be out soon. But in the meantime, you can look at a chapter that introduces the CTLNS and their network dynamics properties, and the paper on the fixed points of CTLNS, which I talked about at the beginning of my talk. And I would like to thank my fellow members in our project group of the Women in Computational Topology, and you all for listening.
Thank you, Alice. Could you talk perhaps a little more about the future work? What the next steps in your project are?
Yeah. So as we've seen before, when we have a weakly cyclic graph, we are able to predict exactly the sequence of the neurons that are going to fire one after the other one, according to both how the cycle is built as the conjunction between different directional graphs, and according to the nodes that are in the periphery and that get part of the action in the firing up. But we cannot do this yet for a completely non-DAG component of the graph, as there might be different cycles interacting with each other, or cycles and clicks interacting with each other, and the structure might be more complex. So we would like to look into what happens when we have more different and complicated structure of cycles that interact with one another, and there is not only an acyclic part of the graph.
Okay, thank you. Are there any further questions or comments? Okay, there are lots of nice comments in the chat saying that you think and hope that this is all very promising, and congratulating you on a very nice paper. Any more questions?
Yeah. So thanks, Alice, for the wonderful talk. Learned a lot. And then just one question. The example you show in the slides were relatively small scales. When you actually have a large scale data, will you face any computational challenge since you're actually doing a graph computation? So I guess there will be some challenge in that aspect.
Yes. So for bigger graphs, for looking for directional covers, right now we have a dictionary of possible directional covers of up to 6 nodes that we look for in the graph. Looking for motifs in a graph, it's an NP-hard problem, so it's going to take a long time for bigger graphs, but there are algorithms out there that can look for specific motifs in directional graphs that can fast can make the computation a little faster. But it's we found that starting with directional graphs that you already know are directional makes it way easier to handle.
So it's basically saying that a heuristic initialization will actually helps your algorithm to speed up. Is that right?
Yeah.
Great. Thanks so much for the talk again. Yep.
Okay. Are there any other questions? If not, then I suggest that we thank Alicia again for a lovely talk.